Kinetic models successfully interpret several experiments carried out under various operating conditions, examining each potential response independently. Using stiffer findings, a lab's continuous pilot was set up in our lab to increase the model validity. A continuous third tank reactor (CSTR) serves as the pilot plant central component compared to packed bed reactor, which can result in temperature profiles within the catalyst in the pipes of visible axis. CSTR enables very good heat exchange at the lab scale, as Lin et al. 2012 recently showed. Temperature profile within the pipe axis in the packed reactor lower the selectivity of propylene oxide. As shown in our research and more recently by Cstr et al., selectivity loss was explained in terms of propylene oxide ring opening event catalyzed by two distinct sites. For relatively small-scale development investigation, the most practical reactor configuration is CSTR. The CSTR can be used any catalyst that is already being used in a stirred tank, and normal technique can be used to convert batch kinetic data into the CSTR train. In the homogeneous reduction of an intermediate in the catalyst of microfractal, Wang has proven the use of CRCR system. We describe here how this strategy was extended to heterogeneous hydrogenation of an intermediate utilized in the product.
Hi, my name is Ainul Sharafana binti Samsul Hayat, and I would like to talk about design of CSTR. The main component of a CSTR include the reactor vessel, agitator, inlet and outlet parts, heating cooling system, sensors, and control system. First, the reactor vessel, typically cylindrical or spherical and made from stainless steel, determines the reactor capacity. Larger volume allow greater production, but require efficient mixing and heat transfer. And next, agitator. Inside the reactor vessel, the agitator plays a critical role. This mechanical device ensure that reactants are truly mixed, leading to a uniform temperature and concentration throughout the reactor. Different types of agitators, such as pedals, blades, and turbines, are used depending on the viscosity and nature of the reactor. Third, inlet and outlet parts. This component is to optimize the flow of reactant and products. Inlet parts control the entry of reactants, while outlet parts allow continuous removal of products and byproducts, maintaining a stable reaction environment and ensuring continuous operation. Fourth, heating cooling system. To maintain the desired reaction temperature, CSTR are quite equipped with heating or cooling systems, which can include jackets surrounding the reactor or internal coils for circulating heat transfer fluids. Precise temperature control is crucial to maintain reaction rates and selectivity, preventing overheating or excessive cooling. And the last one, sensors and control system. Sensors continuously monitor temperature and pressure, and the control system adjusts heating, cooling rates, and agitator speed to maintain optimal condition. This can range from simple PID controls to advanced distributed control system. Next, concept of CSTR. A CSTR functions by maintaining a continuous flow of input and output materials, ensuring a stable operating condition and uniform product quality. Reactants are consistently fed into the reactor, while products are continuously extracted. This continuous flow maintains a balance, keeping the concentration of reactants and product steady, which is crucial for managing large-scale reaction efficiency. One key feature of a CSTR is its agitation or stirring mechanism. This ensures true mixing of the reactants, resulting in a homogeneous mixture with consistent concentration and temperature throughout the reactor. This uniformity is essential for achieving constant reaction rates and preventing undesirable side reaction or product degradation. Next, steady state assumption. The CSTR operates under the steady state assumption, meaning the inflow and outflow rates of reactants and products are in equilibrium. At this state, the condition within the reactor remain constant over time, simplifying the analysis and design of the reactor. Engineers can use mass balance equation to accurately predict the reactor's performance, making it easier to maintain consistent output quality. And the last one, the idealized model. The idealized model of a CSTR assume perfect mixing where the material inside of the reactor is identical to the material existing in it. While real reactor may differ from this ideal behavior, The model provides a valuable foundation for understanding and designing CSTR. So engineering used this model to determine crucial parameters such as reactor volume, residence time, and conversion rates.
My name is Ratana Bemitisari, and as for my part, I'm going to explain about function, advantage and disadvantage of CSTR. Continuous stirred tank reactors, or we call it as CSTR, are widely used in industries for their ability to efficiently mix reactants and maintain consistent reaction conditions. The first function of CSTR is consistent mixing. CSTRs ensure that the contents are well mixed, leading to uniform temperature and concentration throughout the reactor. This helps in achieving consistent product quality. The second function is temperature control. They allow precise temperature control, which is crucial for maintaining the right conditions for chemical reactions. Techniques like PID controllers are commonly used to manage temperature effectively. The third function is handling complex reactions. CSTRs are capable of handling complex, nonlinear chemical reactions efficiently. Advanced control methods such as model predictive control, or we call it as MPC, help manage these reactions by predicting future behavior and adjusting controls accordingly. The last one is disturbance rejection. CSTR can manage external disturbances such as changes in reactant flow rates or temperatures. Model-free adaptive controls and sliding mode controls are used to maintain stability and performance despite these disturbances. In conclusion, CSTRs play a critical role in industrial processes by ensuring consistent mixing, precise temperature control, handling complex reaction, and also rejecting disturbances. The next part, I'm going to explain about advantages and disadvantages of continuous stirred tank reactor, or we call it as CSTR. The first advantage is uniform mixing. CSTRs ensure that contents are well mixed, providing a consistent environment for reactions. This is crucial for maintaining stable temperatures and concentrations, which leads to better product quality. The second advantage is steady state operation. These reactors operate continuously, making them ideal for large-scale industrial processes where consistent production is needed. The third advantage is ease of temperature control. The continuous flow and mixing in CSTRs make it easier to manage and maintain the desired temperature, which is beneficial for reactions sensitive to temperature changes. The last advantage is ideal for liquid phase reactions. CSTRs are particularly good for liquid phase reactions as they ensure through contact between reactants, enhancing reaction efficiency. Despite the advantages, there are also disadvantages. The first disadvantage is large volume requirements. To achieve the same conversion as other types of reactors, CSTRs typically require larger volumes, which can be more expensive and space consuming. The second disadvantage is back mixing. Complete mixing can lead to back mixing, reducing efficiency for reactions where a concentration gradient is beneficial. The second disadvantage is sensitivity to flow rates. The performance of a CSTR can be highly sensitive to changes in flow rates, which can complicate operation and require sophisticated control systems. The last disadvantage is complex control systems. Due to their non-linear dynamics, CSTRs often require advanced control strategies to manage multiple operating points effectively. That's all for my part. Next, I will pass to my friend to the next part.
Hi, Assalamualaikum. I'm Nur Amra Balkis binti Muhammad Qasim. I would like to explain about the application contains the tank reactor. So, CSTRs manage several chemical processes, making them useful in the chemical industry. CSTR have a stable and unstable equilibrium point, making temperature regulation difficult, especially in the exothermic processes, where sudden temperature rises could affect product synthesis and reactor safety. Traditional proportional integral derivative PID controller fails to regulate continuous stirred tank reactor variable operating circumstance due to their rigid parameter. To overcome the issue PID, controller and fuzzy gain schedule have been recommended. The article describes using a genetic algorithm to modify POFID controller setting to minimize absolute error and regulate input changes. Fuzzy gain scheduling using the Takagi-Sugeno model interpolate local controller output in different operating zones. This guarantees accurate temperature management and enhances control system distributed rejection. This new method outperform classic PID controller, making them promising option for chemical industry CSTR modulation. So the next one is the wastewater treatment. The CSTR has a crucial function in the anaerobic digestion phase. When microbial colonies decompose the organic substance present in the effluent, The utilization of MAB precipitation as a preliminary treatment method facilitates the elimination of the ammonia and phosphate from the wastewater, resulting in a decreased burden on the CSTR and enhance the effectiveness of the subsequent aerobatic treatment in the SPR. So in general, the use of CSTR in wastewater treatment has proven to be highly efficient in managing soil wastewater with high level of the pollutant. This is especially true when CSTR is coupled with the MAP precipitation and sequencing batch reactor SBR. So this holistic technique guarantees throughout treatment of wastewater, rendering it appropriate for either reuse or environmentally sound release. Other than that, CSTR play a crucial role in the pharmaceutical and petrochemical sector because they can effectively maintain precise and constant reaction conditions. The continuous still tank reactor are utilized in the pharmaceutical sector to produce active pharmaceutical ingredient with a focus on achieve exceptional purity and quality. This is of utmost importance to comply with the regulatory criteria. CSTR offer a meticulous control over reaction parameters which improve the uniformity and safety of the product. CSTR of continuous still tank reactor are employed in the petrochemical sector for polymerization procedures and enable the production of polymer characterized by consistent features. Due to their uninterrupted functioning and effective heat management capabilities, they are well suited for large-scale manufacturing, fulfilling the petrochemical industry high criteria of productivity. The versatility of continuous still tank reactor in accommodating different reaction and conditions and their capability to function well under high pressure further emphasize their significance in this sector. Let's now discuss the continuous still tank reactor CSTR product and catalyst. Make it a study a continuously stirred tank reactors mesoporous nanonickel aluminate catalyst. The catalytic process produces carbon monoxide, methane, and C2CO4 hydrocarbon. Certain conditions were met in a continuously stirred tank reactor CSTR. In this investigation, a CSTR is needed to create homogeneous reaction condition for assessing mesoporous nanonickel aluminate catalyst performance. The CSTR keep reactant well mixed and maintain reactor temperature and concentration. Continuous mixing optimize CO2 and H2 interaction with the catalyst surface, improving catalyst. The CSTR also finely control reaction parameters including temperature, pressure, and gas outlet space velocity, which affect reaction rate and product selectivity.
Next, feature direction for CSTR. First, flexible reactor design. Reactor design must be improved if particle accumulation and system clogging are to be avoided during prolonged operation. Reducing the reactor's low mass exchange section should be the main priority. Reactor design, flow pattern, or mixing mechanism can all be changed to reduce dead zone and stagnant area where little mass transfer happens. Improving the reactor design is crucial to prevent particle build-up, system clogging during extended operation. The key focus should be on reducing low mass exchange portion by modifying the reactor geometry, flow patterns, mixing mechanisms. Increasing the overall residence times and employing more CSTR modules can lead to higher conversion rate. Expanding the reactor volume or adding more CSTR stage can provide longer residence time and better mixing up, prevent the particle buildup. Implementing strategies to actively manage and remove particles such as improved filtration and sedimentation system is also important while ensuring compatibility between the reactor design, operating condition, and material characteristics can minimize particle generation. Incorporating monitoring system and comprehensive maintenance plan can help detect and address issues early and allowing optimized residence time and particle management to improve the reactor's performance for reliable, efficient, long-term operations. Second, advanced control system. For challenging multivariable control situation, maximum principal concentration (MPC) is a valuable advanced control strategy. A set of computer control algorithm known as MPC employs implicit process model to regulate the plane facial behavior. MPC can be used for nearly any type issue, but it excels situation with a high number of manipulated and controlled variable, modifying control goals and malfunctioning equipment and in delaying time. This day, MPC and linear model repetitive energy dissipation. It is important to keep in mind that increased energy dissipation can lead to higher power consumption in a process when heat exchange is maximized. The cost of heating, carrier use, batch time, and product quality can all be greatly reduced in exchange. It is necessary to process. Lastly, bioprocessing application. The bioprocessing industry has made extensive use of CSTR because of its capacity to offer effective mixing and ideal interaction between the waste stream and the biomass. These reactors are especially useful for digesting high-strength organic waste produced by food processing, brewing, dairy industry, among the other industries. One of the main benefits of CSTR is their low construction cost and straightforward design, which make them an affordable wastewater treatment option. In order to maximize effectiveness of the bioprocessing reaction, optimal heat and material distribution are ensured via throughout mixing within the reactor. Treatment results are more dependable and consistent because of the improved control over the process parameter made possible this homogeneous environment. Moreover, the anaerobic digestion in CSTR produces biogas which can be used partially offset the treatment system operational expenses. The bioprocess business can become more sustainable overall by using the biogas produced as a renewable energy source.